Hi everyone. I am Anuj Kumar from IIT Roorkee, and this is the third problem-solving session for NPTEL course, Colloids and Surfaces. The first question is the interactive energy versus separation distance for a pair of argon molecules. It's shown in Figure 1, and this is the Figure 1 is plotted the interaction energy versus separation distance. Okay, basically. The interaction energy is just scaled with the thermal energy kb, and the separation distance is in nanometer. So these are the units, and here the interaction energy is shown Leonard Jonas potential divided by kbt and the values on y-axis. So basically your value is uh, whatever it is. Let's say this is the term zero point 0.2 multiply kbt, that is the value. Okay, so these are another terms. So from figure 1, identify the line that correspond to attractive, repulsive and total interaction energy. So the dotted lines correspond to, so this is the dotted line that is correspond to, this is a normal question. Okay, so this is basically represent the repulsion, and similarly this represent the attraction, and this is the resultant. Okay, so based on these you have to just put the answers. The dotted lines correspond to repulsive interaction energy. Okay, and the dashed line corresponds to attraction, and the continuous lines correspond to total interaction energy. That is the resultant. Okay, that was a basic question. And now I am going to second question. For the variation of total interaction, repulsive and attractive interactions shown in this figure, you have to pick the expression that best represents the functional variations. So the total interaction, the total interaction, you are already aware about uh, this formula. That is, the total interaction will be, uh, let's say, a x minus 12 and x minus 6. Okay, so this is the uh, representation, or you can say the formula. So this is, you have to select. Okay, so here this is the repulsive term, and this is the attractive term. Okay, so the total interaction will best represents this C well, and second is the repulsive interaction. Okay, so I have already told you this is the repulsive interaction, that is a divided by x power 12. Okay, x, or you can say r, that is the separation distance. Okay, so the f, because a is a on r is equal to 12, and also there is a positive sign that represents the repulsion. Okay, because the energy is increasing with the distance. So the repulsion interaction will be represented by the f term. Okay, and the third is the attractive interaction. So this part is the attractive interaction. So minus a r power 6. This is this value. So g value will be the attractive interaction. Will be representing the attractive interaction. So this was a formula based question. Okay. So I am going to the next question now. Before that, let me see whether. So the next question is, spherical particles hangs on a planar silica surface. So there is any silica surface, and the silica particles has hanged on it. Okay, so let me do the full screen. Hmm. So the van der Waals interaction between them is represented by F is equal to AR divided by 6D square. D is the separation distance. Separation distance. Okay, and R is the radius of the sphere. Okay, because these are the spherical particles, and A is the Hamilton constant. Okay, these are the terminology. And the van der Waals interaction increases linearly with the radius of the sphere. Okay, the gravitational force, the gravitational force is mg, and here only the expansion is rho into v into z. So volume in the case of a sphere 4 by 3 pi r cube rho z. Okay, so this term is given here. So it increases. Let me represent it by fg, and this is the van der Waals interaction vdw. Okay, so these are two terms that is given in the questions, and it increases cubically with it. Yes, it increases cubically because here is the r cube. So this is not a small r; it should be the capital R. And it is capital R in full question. Okay, so as a consequence, the behavior of small spheres is dominated by van der Waals forces, while for large spheres, gravity is more important. Okay, so the small spheres will uh, the van der Waals force will be dominating for smaller spheres, and for the larger sphere, the gravitational force will be dominant. So in the questions, we are asked at which radius is the gravitational force so strong that the sphere detaches. So the sphere detach means there is no force, there is no interaction between this surface and the silica particles. So report, you have to report your answers in millimeters. These are the values. So now I go to the solution. Okay. So this is the term that we are given here. So F is equal to, this is the van der Waals direction, AR by 6 square. Okay, and the gravitational force is given 4 by 3. Okay, so after the interaction there is no resultant force, so you can write here minus Fc is equal to 0. So the resultant force will be 0. That will show there is the spheres are detached from the surface. Okay, so one by one I calculate these terms. Okay, for van der Waals interactions, that is AR by 6D square. The value of A, Hamilton constant, is given here 6 10 raised to minus 20 joule. Okay, and the radius you have to determine, and the separation distance is given here, the zero point 0.7 nanometer, or 0.7 10 raised to minus 9 meter. Okay, so the van der Waals interaction force, so the van der Waals force of interaction will be, uh, you have to put the value of Hamilton constant 6 into minus 10 raised to minus 20 r divided by 6 into 0.17 10 raised to minus 9 square. Okay, or van der Waals force will be 6 r divided by 6 0.17 10 raised to minus 18. Okay, so this will be cancelled out, and r 10 raised to minus 2 and 0.17 so r is equal to point let me calculate this term. 17.17, that is 0.0289. Okay, and this will be 10 raised to minus 2, or you can say 0.0289, that is 34.60 r 10 raised to minus 2. Okay, okay, this is the value of van der Waals interaction force. And if we calculate the Fg value, okay, so first I will just Fg is equal to 4 by 3.14.17 10 raised to minus 3 whole cube. Okay, and the density is given here 5000 kg per meter cube. Okay, so 5000 in 9.8. Okay, so sorry, this is not the r value, this is separation distance. So just calculate these values, and 4 multiply 3.14 multiply 5000 9.8 and divide by 3, that is 20546.6 r cube. Okay, so we have to determine this value. So this term value, that is sorry, it should be this. Okay, so 20546.6 r cube equal to 0.3460 r. So r square equal to 0.3460 20546.6. Okay, so r square is equal to 0.3460 divided by 6.6, that is 169 10 raised to minus 8. Okay, so you can say r equal to 13 10 raised to minus 4. Okay, or you can say 1.3 10 raised to minus 3. So this is meter. Okay, so you have to calculate in mm. Okay, this report your answer in mm. So r equal to 1.3 mm will be the right answer for this. Okay, yes, yes, I will share uh, the solution for this in the different manner. This is for solving purpose here. Okay, so the value for this radius, that is 1.3 mm. Okay, this is a larger distance as compared to the nanometers. Okay, so uh, the next question is, the following table provides parameters that are necessary to calculate the magnitudes of Debye, Kisum, and London interactions that contribute to overall van der Waals interaction between toluene molecules. So here are the values that is given for toluene. So first is the mu value, that is 0.43 Debye. Okay, so zero point 0.3 Debye, that is the dipole moment. Okay, so 0.433.33 10 raised to minus 30 coulomb meter. Okay, let me check the value. Yes, and the another values given here, the alpha, the polarizability, alpha divided by 4 epsilon naught in 10 raised to 30 is equal to 11.80. Okay, so uh, you can rearrange 4 pi epsilon 0 11.80 10 raised to minus 30 meter cube. That is the value for alpha, and the beta into 10 raised to 77 is given 5.16. So beta will be 5.16 10 raised to minus 77 joule meter power 6. Okay, so this is the interactive term that we write for the van der Waals interactions. So this term is for phi d, that is the Debye interaction, and this term will be the Kisum interaction, and this term will be the phi n, that is the London response. So we can write as a in a collective manner. We can write the van der Waals interaction is normally a summation of phi d plus Kisum plus London interaction. Okay, so if I go for the contribution, that is by the individual force. If I talk about this Debye interaction, so that will be 2 alpha mu square divided by 4 pi epsilon square, or this term. Okay, that is beta 1 1. Okay, yes. So this will be the contribution due to Debye interaction. Okay, so let me put these values here. So mu is equal to 0.43 multiplied by 3.335 10 raised to minus 30 coulomb meter. Okay, this is not centimeter, that is coulomb meter. And the alpha value is uh, yeah, 4 pi epsilon naught 11.80 10 raised to minus 30 meter cube, and the beta value beta value uh, is 5.1610 raised to power minus 77. Okay, so the value of all terms is given here. Epsilon naught is at 0.8510 raised to minus 12. So putting all these values here to alpha is 4 pi epsilon naught multiply by 14.80 and 10 raised to minus 13. Okay, and the mu square, that is 4.43 3.33 10 raised to minus 30 whole square. And I am putting the value as it is, and the beta value is 5.1610 raised to minus 77. Okay, so these terms will cancel out, so the resultant will be 11.80 10 raised to minus 30 and 10 raised to minus 60 and 0.43 3.3 square, that is divided by 4 by epsilon naught. Okay, 5.16 10 raised to minus 77. Sorry for the so you can solve this value and get the value of phi d, that is the Debye contribution. You will let me calculate this term, that is 2.11.80 and 23.6 multiply by and 0.433.33, okay, and 1.4319, that is 2.050. Okay, and uh, okay, let me insert one more slide here. Okay, so uh, so phi d equal to 23.6 multiply by 2.050 and 10 raised to minus 30 and 60, 10 raised to minus 9, and expanding the denominator values, that for 3.14 8.85 10 raised to minus 12 and 5.16 10 raised to minus 77. Okay, so 23.6 2.50 10 raised to minus 90. Okay, and let me calculate the lower value for 3.14 8.85 5.16, that is 573.56 multiplied by 10 raised to minus 89. Okay, calculating again, 23.6 multiplied 2.050, that is 48.38, 10 raised to minus 19 plus 89 minus 1 and 473.56. Okay, So divide by 5, 73.56. That is 0.084 10 raised to minus 1. Okay, and you can write 0.0084. Okay, so this is the contribution. So this is the contribution from Dubai. Okay, that is the 5D. So this is the contribution, and what the question asking that you have to calculate Dubai at 4 nanometer separation distance. Okay, so as you know in beginning, so here you can say this is the separation distance. Okay, so this factor does not have any unit, so if I multiply by beta divide by the separation 6. Okay, so I think there will be no impact on the unit, that is joule meter 6, that is meter 6. So you have to just calculate the answers in joule. Okay, so point 0084 multiply by uh, 5.16 10 raised to power minus 77, and the separation distance is zero point 0.4. Okay, nanometer. So 10 raised to minus 9 whole power 6 0.0084 5.16 10 raised to power minus 77 divide by zero point 0.4 raised to 6 and 10 raised to minus 54. Okay, so the value will be 0.0084 and 5.16 divide by, well, let me calculate, zero point 0.4 whole power 6 zero point 0.4 zero point 0.4 is 0.064, that is point uh, 004096, and multiply by 10 raised to minus 77 plus 54. Okay, so 0.0084 multiply by 5.16 divide by 0.004096, that is I'm getting 10.58 10 raised to minus 23. Okay, or sorry, 1.058 10 raised to minus 22. So this is the uh, you have to just select the closest value. Okay, so this will be, I think, the right answer. Okay, you can again check the value. Okay, and the next question, you have to calculate the key sum term. Okay, so similarly, for the key sum term, you have to 5k, that will be equal to 2 by 3 mu 1, or you can say mu 4 divided by kbt, that is 4 pi epsilon naught square. Let me just confirm this value, 2 by 3 m4 kbt 4 pi epsilon naught square. Okay, and beta 1. So this will be the contribution due to the key sum interaction. Okay, so uh, you know this term, you already know, and for kb you have to put 1.3810 raised to minus 23, and for temperature 298 Kelvin, and all the values are given in the question. Okay, so you will calculate the contribution due to the key sum interaction, and after that you have to just multiply the answer by beta and divide by x6. Okay, so you will get the value accordingly. Okay, and for the London dispersion value, uh, so for total van der Waal interaction, there are three terms, that is phi d plus phi k plus phi l, and the contribution of total addition will be equal to 1. If you know these two values, okay, let me just put the values. Uh, let's say if I got this value for this term, and plus for 5k I am getting 0.001, and plus 5 is equal to 1. So you have to just minus the value from 1, and you will get the value of London dispersion. And after that you have to just similarly you have to multiply by uh, beta and divide by x6. Okay, so this will be the value of London dispersion at zero point 0.4 nanometer separation distance. After that, this is the next question. You have to calculate the van der Waal interaction at 4.4 nanometer separation distance and report your answer in joules. So, in this particular question, what you have to do, the d value, about the key sum interaction, about the London dispersion interaction, and you have to just add those values and multiply by beta and x power 6. So for x, you have to put 0.14 10 raised to minus 9 meter. Okay, so this additional term is introduced here only for uh, to get the answer in joules, because the unit of beta is this, and whenever you will divide the value of divide the meter power 6, so these will be cancelled out and you will get the answer in joules. Okay, so I think that will be very clear now. Okay, so uh, this will be the right answer for this, as I have already solved. Okay, I will provide the detailed solution also. Okay, so I will just putting up the summary of this question. This is a very important question. Okay, yes. So in this particular questions, these three terms are given. Okay, first is the mu, second is the polarizability, and third is the beta. Okay, so from this expression you have to just know the contribution of different terms. Okay, because the total van der Waals interaction is contributed by three terms, that is first is Debye, second is the Kisum, and third is the London dispersion forces. Okay, so you have to calculate the individual one. You don't need to calculate the individual one. You can calculate two, and third one you can just get uh, by subtracting these two values from 1. Okay, because in the if I go for the expression of London dispersion, you will get phi L equal to ph by nu, ph by nu, and 4 pi epsilon naught square, okay, and the alpha square, okay, and multiply beta, okay. This beta 1 is beta, okay. So this value, you have, a Planck constant is, but the frequency is unknown. So in this particular question, you can get the value of London dispersion forces by simply subtracting from one, okay. And after that, what you have to do, you have to just put the values in this simple formula, and uh, you will get the contribution, okay. So uh, after getting the contribution, you have to, because the question is asked, the value is asked in the joule, so you have to just multiply by this beta value and divide by x power 6. That is the separation distance, okay. You will get the phi t, phi k, and similarly you will get the phi l, okay. After the calculating these three interactions, you have to calculate the total van der Waal interaction. So for that, well, you have to just add these values and multiply. Similarly, for multiplied by beta divided by x power 6. Okay, so you will get the this value. Another question is I have taken from the DLS experiments. Okay, so the dynamic light scattering experiment is carried out to measure the size of colloidal particles dispersed in water at a temperature is given here, T is equal to 293 Kelvin, and the viscosity is given here 0.001 Pascal second, and the density is 1000 kg per meter cube. The following data for the correlation function, okay, is given here. So the S here is the scattering vector, okay, and T is the time delay time. Assume the particle to be spherical in shape and that the instrument constant in Segert relation. I will go for the Segert relation to be equal to 1. Okay. So what is the relation? That is Z to ST 1 plus. This is the instrument constant, and the G1 ST square. Okay. So uh, the instrument constant in this relation is given to 1, so you have to put out the value of instrument constant is 1, so g2 st is equal to 1 plus g1 st square, okay. So you can subtract g2 st minus 1 and you will get g1 st square, and for the value calculating g1, you have to just under root g2 st minus 1, okay. So in this next slide, I have done the same work. These are the values, okay. So these are the values given in the question, okay. I just uh, first minus the value, so 1.75 minus 1, 1.75, so so on, every value is getting by the fact subtracting by the factor of 1. After that, this value, if I under root this value 0.75, I will get 0.866, okay. So that will be the g1 value, auto correlation function value. So uh, so s squared t, okay. So if I take this as x axis and I take this as y axis, so I can easily draw a curve using excel, okay. So I will get something like this. So if I so on y axis, that is g1 st, and this is the value of a and e. So this value, because we have put s square t on x axis. Okay, so this value is the diffusion constant value. Okay, I have not included this 10 raised to minus 10 in this curve, so you can just compensate for that. So the 0.288 into 10 raised to minus 10 will be the value of diffusion constant. Okay, so this is basically the application. From the autocorrelation function you can just get the value of diffusion coefficient. So this value okay, so this question is already asked, what is the value of diffusion coefficient from the given data. Okay, so this is the value and the unit is meter square per second. So 0.288 into 10 raised to minus 10 meter square per second will be the right answer for diffusion constant. Okay, so this was a basic question. And from this data you have to calculate the hydrodynamic radius in nanometer. Okay, so you have to just put the old formula, that is kbt 6 pi mu r, and you have to calculate this term. So r is equal to kbt divided by 6 pi mu d. Okay, so 1.3810 is to minus 23, and for temperature 293 Kelvin. Temperature is given 293 Kelvin here, and 6 multiply 3.14. Viscosity is given point, point 0.001, and the diffusion coefficient is 0.288 10 raised to minus 10. Okay, 10 raised to minus 10. Okay, so just simplify this numerical problem. So 1.38 multiplied by 293, that is 404.34 10 raised to minus 23, and 6 multiplied by 3.14 multiplied by 0.001 multiplied by 0.288. That value you will get the 0.00542 into 10 raised to minus 10. Okay, and divided by 40.34 divided by 0.00542, that is 74601 10 raised to minus 30. Okay, or I can say 7.4601 10 raised to minus 9 meter, or 7.46 nanometer. Okay, so this will be the right answer for this. So I am repeating again this question. Okay, so a dynamic light scattering experiment is carried out. Okay, so you know this expression here. So G2, that is a function of S and T. S is the scattering coefficient, 1 plus epsilon, or this is Chi, G1 ST whole square. This is the instrument constant. The instrument constant is equal to 1. So G2 ST 1 plus, So g2, arranging this term, g2 st minus 1 is equal to g1 st square. And for from this expression you can just calculate the value of g1 st by taking the under root of this g2 st minus 1. In question you are given the values of g2 st, so you have to simply uh, subtract minus from these minus 1 from these values, and you will get the values of g1 st after taking the under root. Okay. And s2 s square t multiplied by 10 minus 10, these are the values here. You have to just put these values on the x-axis. Okay. And you plot a curve. By plotting a curve you will get an equation like this. And after that from the for the help of this from the help of this equation, you can just calculate the diffusion coefficient. Okay. So the diffusion coefficient value we are getting the 0.28810 is to minus 10 meter square per second. And from that you can simply calculate the hydrodynamic radius of the particle. Okay, by using this simple formula, that is d is equal to kpt by 6 pi mu r. So mu is the viscosity, that is also given here. R is you have to calculate. T is the temperature, you have this is already given in the question. And the Boltzmann constant is already given, and the pi value is 3.14. Okay. So this is all about the